Hi, my name is Thomas Lin with the University of Toronto, and I'm here today to give you guys a hands-on walkthrough of how to set up a VXLAN tunnel between two OVSs, or Open Virtual Switches, on the Savi testbed. So uh, to begin, if you guys haven't already, you should have created two virtual machines on the Savi testbed using the EC1508-overlay image. So if you haven't done that, you can pause the video and do that now quickly. So if you guys haven't gone through the overlay parts of this lecture already, please do so now. I will assume you already know what an overlay is and what VXLAN is. So VXLAN tunnels using Open vSwitch. So OVS itself has support for tunneling using the VXLAN protocol. One thing to note is that by default, these tunnels are unidirectional in nature. So if you actually want two OVSs to be able to communicate with each other, then each OVS must individually initiate a connection with the other OVS switch in order to establish bidirectional connectivity. So, and also in order for end hosts to be able to access the overlay itself, they have to create what's called an OVS internal interface. And these OVS internal interfaces are basically interfaces on the switch that quote unquote face inwards to the operating system, such that any packets you send to that interface goes directly into the switch itself. To illustrate this, here's a picture of a two-node setup that is connected, interconnected using VXLAN, right? So in this setup here, the red part corresponds to an internal interface, and the purple part here corresponds to a VXLAN interface. So by default, when you set up a VXLAN interface from one OVS to another OVS here, they'll be able to have bidirectional connectivity over the underlying network, right? But as I mentioned, in order for a host to be able to actually access it, they need to set up an internal interface to allow them to send traffic to and from the OVS. So once they set up these internal interfaces, then you should be able to send packets to the internal interface out of the VXLAN interface through the underlay network into the VXLAN interface of the second OVS and then out of the other host's internal interface. So when packets when packets in OVS1 here on the left exit the VXLAN interface, what happens is that it's actually being encapsulated into a UDP packets in layer 4. And then after it traverses through the underlying network and it enters into this VXLAN interface on the right, when it enters into the OVS, it gets decapsulated. So in this way, when the packet exits this internal interface on the right here, you see the original packet that host 1 sent. So as I mentioned, because VXLAN operates over UDP, you need to open up UDP in your security group rules. So if you haven't already, you need to open up UDP port 4789. That's the default port that OVS uses for VXLAN. In Nova, you can simply run a command such as this. So I'll give you a moment to do that if you haven't already. One thing to note is that if you've already started the lab and you've already run that NetSoft-overlay-init script, it should have already populated your security group with UDP port 4789 and opened it up for you. So let me go to my terminal here. So let me see what security groups I have here. So I have a security group called NetSoft 50, which was created by that init scripts that you run at the beginning of the lab. And if I go Nova security group list rules and I run NetSoft 50, I can see that yes, that script has already populated UDP ports 4789 and opened it up for me in this security group. So when I actually create virtual machines, I need to create them using this security group. So let me get 2 virtual machines right now, and then we will continue with this hands-on. So let me quickly do that. So yeah, so in our terminal here, if I do Nova lists right now, I can see 2 virtual machines. So these 2 virtual machines overlay H1, overlay H2. So right now, these are just bare virtual machines that were boot up using the ECE 1508 image. So let me shrink this a little bit. Right, you can see that the image uses the ECE 1508-overlay image. And in my security groups, I have NetSoft 50. So that UDP ports 4789 should already be open. So if I come back here, the first thing that we have to do is that in each switch, in each host, we need to create an OVS within each host. So let's do that now. So to do that, I can run sudo OVS vsctl add bridge and then the name of a bridge, which is completely up to you. One thing that is optional here is that you can add the -- may exists flag. And all that flag does is that it ensures no error message if an OVS with that same name already exists. And I'll demonstrate that here shortly. So if I go back here, let me SSH into one of them. So I need the IP address here, which is 10.12.1.22.3. Default password is Savi. So let me name this H1, and then in another terminal, I'll go .4 Savi. Now name this into H2. So for example, right now if I do sudo OVS vsctl show, which should show all the OVS switches within this VM, I see none. But if I do add bridge and I'll call it H1VR, so this is the name of my bridge that I'm going to create. By the way, if you see this message, ignore it. That's completely fine. The commands you run should still have completed successfully, unless you see more error messages. So now if I do show again, I'll see there's a new bridge that was created, right? So normally, if let's say you already have a bridge, and then you try and add another bridge with the same name, you'll get an error message, right? But if you add dash may exist, then you don't get an error message. Basically, that dash may exist is telling OVS this bridge may already exist, and if it does, just don't do anything, right? So let's do this again in the second host really quickly. So for this one, I'm going to call my bridge H2-VR. So again, if I do show, I should see a bridge here. So now that we've created a bridge on both ends, let's create the internal interfaces, right? So again, this internal interface is simply an interface that is internally facing. So what does that mean? So right now, say for example, in H1, if I run ifconfig, right, or ifconfig-a, you'll see a number of interfaces. Not all of them I can use, but you'll see, for example, loopback ETH0 Docker. Ignore this for now. You'll use this in the next lab. This essentially just represents the bridge itself. It's not well, it is in essence an internal interface, but you don't want to use this one for now. So if I go sudo OVS vsctl, I can add another ports, right? And the format for adding another port is add ports, the name of the bridge, and then an interface name that is up for you to decide, -- set interface with the same interface name, and then you say type equals internal. And here's an example here. So I'll do that here quickly. So add port, my bridge name, which is h1-br, and I'll say h1 internal. I'll say set interface h1 internal, type equals internal. So if I do vsctl show again, you'll see now there is an internal interface created here. So I'll do the same thing really quickly here, but I will add it to an internal interface within the second host. I'll call it h2 internal. So again, I have created an internal interface here. So you may be wondering right now, isn't there already an internal interface here? And you also saw it back here with an internal interface with the same name as a bridge? Yes. So by default, when you do create the bridge, it does create one internal interface for you. But you shouldn't always rely on that. I have seen issues in the past where when you try and use that, I don't know, there's some funky issues going on when you use the default internal interface that's created for you. From my experience, it's better to just create your own internal interface and work with that instead. So right now, when we so now that we've created the internal interface on each switch, let's create the VXLAN interfaces. So when we create the VXLAN interface, we need to specify what is the destination that we want to send these VXLAN messages to. Because remember, when a packet gets encapsulated within a VXLAN packet, which is essentially just a UDP packet, we need to send that packet somewhere. So when we're creating this interface, we need to specify the destination that we want to send these encapsulated packets to. So in this case here, it's another add port command. And again, the first parameter is the bridge name. The second is the interface name, which is up to you. And again, we use set interface with the interface name that you chose. But instead of internal, it's type equals VXLAN. And then we also have to append a certain number of options. So options is the remote IP. So this is the destination that we would like to send the encapsulated packets to. And the second option is the VNI, or the VXLAN network identifier. As an example, here's a full command here. So I'll do this now. So first of all, we need to know the destination IP. So in H2, or host 2, the destination IP, and this is the underlay IP, is 10.12.1.22.4. So in H1, when we're creating that VXLAN interface, we need to use that as the destination IP, or the remote IP. So let me run that command here now. So add ports. Again, we're adding this to H1BR, and I'm going to call it H1 VXLAN. I'll say set interface H1 VXLAN type equals VXLAN. Options remote underscore IP. So that's an underscore, just so you can see. Remote IP equals the underlay IP address of host 2. And options key, which is the VNI. I'll use and you can use any number less than whatever 2 to the 24 is, because the VNI is a 24-bit field. So that's about 16 million. So anything from 1 to 16 million you can use, basically. For the purposes of this demo, I'll just use, say, 2000, right? So key equals 2000. So now if I do show here again, I'll see a VXLAN interface using key 2000 sending any encapsulated packets to this IP address here, right? So this establishes a unidirectional connection only. In order to have bidirectional VXLAN connectivity, we need to do the same thing on host 2, telling it to creating a VXLAN interface there that sends encapsulated packets back here to host 1. So let's do that here. And to save my time, let me do a quick copy and paste. So again, H2, H2, H2. So remote IP here should be the IP of H1, underlay IP, which I can see here is 10.12.122.3. And importantly, we use the same key. So we use the same key such that when H2 sends an encapsulated packet to H1, when host 1 sees that the incoming packet is using key 2000, it'll know that it should be received by this interface. So keep that in mind, because a single Open vSwitch may have multiple VXLAN interfaces, each VXLAN interface is going to a different remote IP, right? And so when you do that, when it receives a packet and it sees that it's coming from this, and it's coming, the packet is coming from a source IP address that matches this with this key, it knows that it was intended for this interface itself. So now that we've established a bidirectional connection between two switches, right? We've essentially finished setting up the tunnel. So now that we've finished setting up the tunnel, how do we use it, right? So just because we've set up the tunnel, we now have to enable the internal interfaces. So we've created the internal interfaces, but we haven't configured them yet. So right here, if I go if config, say port H1 internal, right? I can see that the status is down. It's not up. It has no IP address. So what do we want to do? So we want to configure an overlay IP address for it. So for the purposes of this tutorial, I'm just going to use, let's see, for the purposes of this tutorial or this hands-on walkthrough, I'm just going to use something in the range of the 10.20.30/24 CIDR. So for the first VM, I'm going to assign it an overlay IP address of 10.20.30.100. For the second, it's going to be 10.20.30.200. And the very important step is that you want to set the MPU or the maximum transmission units of the interface to 1450. Why? Because VXLAN will encapsulate your layer 2 packets within a UDP packet. So you have to take into account the overhead introduced by that UDP packet. So that's going to be a UDP header, an IP header, and a separate Ethernet header. And altogether, that should add up to roughly 50. So setting the MPU to 1450 will account for the overhead. If you don't do this, right, and you leave the MPU as the default, say 1500, then after it adds that UDP, that extra UDP, extra IP, and extra Ethernet header, the actual frame size will be larger than the underlay network's MPU, and your packets may be dropped. So to set it, let's set the IP addresses and MPUs for the internal interfaces. So, oops, okay. If I come here, Let me do sudo ifconfig h1 internal, and I want to set host 1 to 10.20.30.100. I'm just going to use a /24 cider. I'm going to set the MTU to 1450, and I'm going to say up to bring the interface up. So if I see the interface again, I can see that the status is now up. I can see that the IPv4 address is 10.20.30.200 with a /24 cider. And I can see that the MTU is 1450. So again, let's do that here. So I can do sudo ifconfig h2-internal. I'm going to set this one to 10.20.30.200 again with a /24 cider. So MTU 1450 and up. So if I see ifconfig h2-internal, I can see it has the IP address I set, a cider of /24, and an MTU of 1450, and it is up, right? So now let's test. How do we test? Well, let's just try a single ping. So once you've set up this overlay IP address, it should have automatically added a routes into your routing table, and it'll say anything destined for this network 10.20.30 with a /24, use this interface here. So let's try pinging the overlay interface on H1, which has an IP address of 10.20.30.100. So if I ping that here now, I should see that I have connectivity, right? So let's see. So how do I prove that this is quote unquote real, right? So to prove this, let me split this screen. So this is, let me make this slightly smaller. So this is H2 pinging H1, pinging specifically the overlay address. So to show you that this is being encapsulated, when packets enter, so let me go back to the image here. When packets enter ETH0 here, it should still be encapsulated in a UDP packet, right? So let's do a TCP dump in H1. And let me dump on interface ETH0, and I'm going to filter for UDP packets. And you can see here that it is successfully, let me make it smaller. Actually, let me close, oops. No. Boy. Okay, yeah. So I can see here when I'm TCP dumping on ETH0 of H1 that it is successfully capturing VXLAN packets. It's telling me that it's a VXLAN packet with a virtual network identifier of 2000. And because TCP dump is able to parse VXLAN packets, it's able to parse it and say that it came from an overlay address of 10.20.30.200. And it's an ICMP echo request. And similarly, on the reply, it can parse the VXLAN packet here, and it can see the overlay addresses, and it can see that this is an ICMP, sorry, echo request, and then it can see that this one is an echo reply. And just to prove that this isn't all just magic, if I stop the ping on this side, you should see that on this side, everything stopped. So yeah, so this essentially, this quick hands-on walkthrough basically shows you how to set up this simple two-node overlay where you connected two OVSs through using a bi-directional VXLAN tunnel. And also, additionally, in order to be able for a host to send packets to and from the overlay, you would have to create internal interfaces and assign them overlay IP addresses. And again, keep in mind when you do that, set the interface's MTU or maximum transmission unit to 1450 to account for the extra VXLAN overhead. So yeah, if you have any questions about this or anything, please post on Piazza. And if not, then thank you very much. Yeah.